I would like to start by thanking all the organizers for giving me the opportunity to present my work and share my perspective. But before that, I must share my screen, right? So let me do that. Okay, here we go. I will not spend time in reading out my title and who I am because Dave did the job already, and I'm humbled by your introduction. Thank you so much. Uh, but I must do something which is very, very important, is to acknowledge the people who actually do the work. And essentially my group members at Indian Institute of Science, Bangalore, these are a bunch of graduate, undergraduate, and highly talented postdocs who are the actual the workers or the one who has created the what I'm going to show you today. And of course, the funding agencies, which were very liberal in funding us, essentially DST Nano Mission, Department of Science and Technology, India, DST Korea, this is a collaborative project, and some of the computers which we have used to generate the data and carry out the modeling. Okay, I think this slide is very redundant because, and I believe it's not needed for this audience. Just to run through it, essentially, like Rebecca said, we are looking for the pattern in the data. And once we identify that pattern, we are going to use it to predict the new future using the data. One of the first applications, at least which I got aware of, was a spam filter, right? You open your email very nicely, a classification model is there, which tells you which one is your spam and which one is your ham. And then when we reach office, we get very quickly bored and we open up some of these video sharing sites, right? And then many times within the first page or just first or second row, you don't go beyond that. And the recommendation which they give you is fairly matches with your choice. And we enjoy watching them. And then if you get a little further bored, then you could go and do some shopping. There again, most of the recommendations, we don't go beyond the recommendation, which is true with the Google search also. So this is the power of machine learning, which has been used by the e-commerce companies. And it's no longer limited to just the e-commerce companies. It's every company, whether it's a manufacturing or airline industry, any industry you name. I mean, fin service, financial services, they are all using the machine learning. And it is being said that if any company which does not have a program on analytics, they are blind, so they don't know where the future is going. So there is no exception. So if it works so well for industry, of course, there are some caveat here. We have to remember the moment actually we go on internet, we ourselves become the data. I mean, our attention become a data. And that's what some of the geniuses sitting behind these computers and trying to figure out how to how to keep your attention on their product and then cleverly direct you the things from where they can make money. Anyway, today's talk is not about that, and this is an ongoing discussion, and you all are aware now. It's all over the news. But what I'm going to tell you that seeing the successes, but we must admit that machine learning does work. So seeing this, it came to the materials a little late when President Obama in 2011, he announced this materials genome initiative in the United States in 2011, wherein the aim was to essentially accelerate the discovery. So most of the devices which you see or anything around you has some material, right? And these are optimized for their particular applications. And they've been discovered, they've been deployed for the particular devices where you are interested in. So from the lab to a product, it takes nearly 2 to 3 decades, including lithium-ion battery. Because of that, we have these smaller devices, or all the transistors which came out of the silicon, right? And this, all of it has taken minimum 20 to 30 years. So his idea was, can we accelerate it? If we can understand the materials genome, can we accelerate this entire process? And that led to a huge initiative, not just from United States. It went to Japan, Europe, Korea, China, and India. And now it's almost, I'm talking about this initiative within, almost 10 years officially. Of course, people were working on it even before this initiative was there, but the aims were different. So a natural question to ask, what did we gain so far? We are not lucky as these internet companies, because where the data almost comes for free. Whereas in scientific community, we need to generate this data, right? Either through experimentally or through the computational approaches. And this is expensive process. And ever since science started, people have been generating data, but they were not very careful in keeping it or in a particular following a particular protocol, because they never thought that they, you know, many times you go to some of the labs are very meticulous, but it's still to use this data for a particular purpose is a really daunting task. And things changes as the time changes, the instruments gets better, the, you know, the environment, even, you know, the global warming is kicking in, so temperature can be very different from when a student 20 years ago took some data, and some another student which took the same data after 30 years later, and in future also. So far, the one tangible which we have already got from this Materials Genome Initiative is various databases. So there's a huge amount of databases which has come out of these through this initiative. And as a material scientist, as experimental material scientist, if you are tomorrow going to work on a given material for a particular application, you would be able to get all the basic informations which you need for that material. It's almost guaranteed in one of these databases. I would not say completely everything you can get here. Of course, I mean, human brain is still, I believe, is smart in, I mean, and they are extremely creative, so they can come up with a newer concept of generating a completely different class of material which nobody had ever thought of. So those you may not get, but, you know, as in a more simplistic approach, if you go, so these are some of the databases which I have listed here. Unfortunately, things in India started a little late, especially for the Materials Genome Initiative. So I was a little bit perturbed by that, you know, because everybody's doing it, why we are not doing it. And then competing with these databases, of course, Materials Project started from MIT, A-Flow from the Duke. They have a huge amount of resources, right? So Materials Project was developed by almost 50 computer scientists, and I'm a humble professor here in ISC, so I can't compete with them as period. But what I could do, I could contribute to it, right? So I need to, and to be relevant, or to get some attention from the community, I needed to find also something which is unique, which has not been done so far. So we created a first functional materials database. We call it a MXene. It's the world's largest 2D materials database. So MXene is a class of material which comes from the max phase by removing the carbon or nitrogen atom which binds it together. So it's a 2D material. So now, as you probably know, the next generation of devices which will come, they will come out of the 2D materials. There's a huge amount of research and attention is being paid currently to find out the most promising 2D materials, from not just from the science perspective, but, you know, from the science to all the way to its application. So we created this data and we call it Anant. I think some of you know the meaning of Anant. Anant is infinity. And the idea is we hopefully one day we will, you know, relatively infinite number of data points we will have here. So right now we have one app open. So this is from public money. So whatever we do is available for everyone. So which contains about 23,000 data points of MXene. So you go on and click and get the whatever basic information you need. But this is a calculated database. For example, the band gap, band structure, what is the atomic structure of this material, because these information can give you a very first, will help you to make your decision in the very beginning. Let me see, there are some Q&A. Okay, anyway, it doesn't matter. So as you could see that Anant actually put us our database on the map of the various databases which are available. There is one more database which will pop up here, but it's actually a mirror of a database which is in Switzerland. Anyway, so this was good. And this is one area where I want help actually, because this is probably the only platform currently exists in India through which we can share the data. And I am limited by resources, so I would be very happy to get help from the community, both from industry and academia, to make it a better and better platform to share and disseminate the data. Okay, now we come to the main part, which is basically what we do with this data. So first part, where my domain knowledge will come in, right? Otherwise, you know, yeah, you don't need to wait 2050. Even the Nobel Prize this year would have gone to uh, to AI. I mean, I'm not. I'm just joking. But at some point, I'm a material scientist. I'm a physicist by training, so I need to bring in my domain knowledge, and that comes when we look at the feature selection. Our data is not as simple as what people go and click on, Facebook, and easily you can. There is just one single variable, the different complexity of the brains and your emotions, your attentions, which they can take it as a features or your attribute, and based on that, they will predict. Or sometimes, you have certain type of personality trait. There is another guy also have a certain type of a personality trait, and you both would, and he watches a certain kind of a video or advertisement. So here you go. Maybe you can also watch, and many times they're right. But in materials where it's not like that, it's very, very different. So here you must understand, what are the things you like to feed to your model, and that is essentially the extraction of the feature itself is a big deal. And what our principle here is, because eventually, even though we are generating or creating these models, our ultimate customers are experimentalists. So we want them to use that because we want to save their resources or their effort. So these model has to be very simple, and these features should be as simple as possible. If I need to do another PhD to learn how do I select the features or attributes, then I'm done, right? I would not ever use it. I just go to my lab and do some trial error or whatever my intuition and carry out my experiments. So we keep this point very much in mind, that it has to be extremely simple, extremely intuitive for the people who may not have the domain knowledge yet can go and use it. So we rely for all the features which we get from in the good old periodic table, because you go there, periodictable.com, you can get some basic information of each element which goes in a formation of a material. Just feed those information and would be enough for you. Okay, a little bit about the structure, which does not require a lot of training. I was looking at my daughter's textbook. They know that they learn a structure in their high school. So that's another label of knowledge, and a little bit more, some small calculations. Maybe you can ask some of your laboratory friends or collaborators to carry out some computation, but not always required. Okay, so if you take these as your ingredient and start building up the model. So first question as a material scientist, if any materials is given to you, if you are working in the field of functional material, you would like to know whether it's a semiconductor or metal. Okay, metals are the one which will conduct electricity. Semiconductors are the one which does not and has a huge amount, because it does not conduct electricity, but you can control its conductivity, and that opens up the entire possibilities for the various applications. So the first model which we built was, I will not go into the details of any of the models, but if you have a question, please write to me and I will be more than happy to discuss with you. So the first thing we did, we generated a classification model, which can, if you provide certain attributes of your material, it can tell you whether it's a semiconductor or metal. So suppose I'm interested in a solar cell. I like to make a solar cell out of MXene, then I need a semiconductors. So I would go and ask this question: can you tell me which one are semiconductor and which one are metal? I can get this answer really quickly with an accuracy of 99%. Here is a ROC, or receiver operating characteristic. This is I'm showing you just to put things a little bit in perspective. So suppose if I'm tossing a coin and trying to get to predict which one is a metal and which one is semiconductor, I will have this red line, right? So this is when you don't have any decision process, right? Now, when you start making decision based on these features which you have incorporated, you start pushing this line towards, closer and closer to one. So the area under the curve, which gives you the accuracy of your model. And so this is the part where, again, you need human. This, I believe, is very difficult for any computer to tell you what are those features should be. Once you have a collection of features, it will help you to select the most important ones, but you need to bring out what are the important features, what are the features, or give the search space to your computer to find out the most important features for your model. I will not sell either the human part or the machine part. I'll tell you the role of both the parts. Okay, So and the next question, once you learn that, okay, this is a semiconductor, you want to know whether its band gap lies within the optical range or not. So that leads to another regression model. And we developed that model, which was a GPR model, which predicts the correct, accurate band gap of these MXenes without any problem, right? And it happened. So if suppose I have to calculate the band gap of those 25,000 MXene, it will take nearly 3 decades to complete that job. Now using this simple model, it will happen in fraction of a second. So this is the power of AI. It's just the way it accelerates things. But the many time you may not believe it. Of course, it will predict the band gap. At the same time, it will also give you the uncertainties. So anyway, machine learning is not meant for getting a single answer, right? So sometimes it may work, sometimes it may not work. So you have to understand that. But there is a huge amount of chance that it will work, and it will save a lot of time. So as an experimentalist, I searched through those 25,000 MXene and ended up finding uh, 20, 30 MXene, which have a property which is good for a solar cell material. So next question was, does it make any sense? All the features which my model has selected, do they have any meaning? I mean, some of the features you will say they have a more importance than the other features, and actually they do. I'm not sure should I go through this because it involves a little bit of knowledge of physics. I'm not offending you. I think you all know that, but it will require a bit more time. But all I want to say that the physics of you can work out actually back engineer the physics behind it. Why certain features are better than than the others, and that exactly follows your intuition. So actually, it was inbuilt from the beginning itself, right? We have done this work already. We have used our intuitions to feed the attributes or features which were important for the prediction of the band gap. So naturally, we were expecting that it must be having some correlation, right? We did not pick up, the country of a particular material where it was found. That has no relevance, right? We have picked up for example, the volume of the unit cell, boiling point, melting point. So these, because they have the attributes of the bonding strength, right? And that those strength gets translated into the band gap. So this part actually comes from human. Next thing, once you learn the band gap, then there are so many applications. I told you, these are functional materials. So semiconductors are beautiful materials that you could do, make electronic devices, you can do photovoltaics, you can do photocatalysis, you can do defects. Our whole electronic world is controlled by the semiconductors. So wherever, or the optoelectronic world. And now the photocatalysis with splitting the water by using the sunlight. So, but for these, you need to know for your material now, there is a band gap, right? There's a conduction band and valence band. So where are these two bands in a universal absolute scale? Because that's very, very important, because you have to compare it with the redox potentials in this case, with the defect transition level in this case, and you have to align them with the whole transport, electron transport and absorber layers if you're making a photovoltaic cell. So this is an important knowledge, and we want to know that. So what is the, where is my VBM and CBM before I go and make a solar cell out of it? So this is the third model which we developed, which can quickly tell you the accurate, which can accurately positions those VBM and CBM. And now your job is, whatever information you needed to get a photocatalyst, or to get a electronic material, or to get a solar cell material, is now answered. You pick up and now you try it in your lab. And of course, we'll tell you the uncertainty also. So that's a simple way. Of course, there is one more layer, which is active learning, which Dr. King already discussed. We are also working on it, but today, in the interest of time, I'll not go into it. Where we actually start with a property and optimize the material. So we go reverse direction. Other approach, which people have been using in both in experiment and theoretical part, is a high throughput based materials design. What you do, you start with a bunch of materials, huge amount of materials, and then let them pass through certain exams or filter or screen them out. So in this case, we applied certain features without going into the details. And then what we found, and our search here was high thermal transport based material, and low thermal transport based material. Why are these two regimes important? You need a ultra high thermal conductivity material because you want to use them in for a cooling application. You want ultra low thermal conductivity material because you want to protect something, right, from the heat. And also you want to use or harvest the waste heat energy to electrical energy using what is known as a thermoelectric effect. So for these 15 ultra-low compounds which we have got are considered as very, very important, and 11 ultra-high thermal conductivity materials which we got are very good for the cooling application. But to develop this or to carry out these high throughput calculations, it took us more than 2 to 3 years, right? And we ended up generating a huge amount of data. So natural option is, can we do some machine learning with this? Because calculation of thermal conductivity or estimation of thermal conductivity is extremely time consuming process and resource extensive process. So we wanted to minimize that effort. But this time, features we picked based on again our intuitions, not going for, and this time we did not go even, we use even a higher level of features. For example, we used phonon spectra, which we had for the previous, so this was one of our filters. We also used and found some correlation. We use Grunheisen parameter because that was the only one within the quasi-harmonic approximation which carries some of the n-harmonicity. Just to tell you, most of the interatomic interaction, which you probably all know, we draw it as a parabola, right? But in reality, it doesn't follow parabola, it deviates. And this deviation from parabola is called n-harmonicity. And if you don't have this n-harmonicity, you will not have thermal transport. Thermal transport of a material will be infinite. So whatever heat will go, it will just pass through it, but that's not the case, right? In real crystal thermal, nothing has an infinite thermal conductivity. Similarly, if you had this parabola, which is just a harmonic approximation, then we will never have a thermal expansion, but that's not true, right? So in reality, we do have an harmonicity, and that is very hard to capture. And one of the parameters which captures is a Grunheisen parameter, and we found that this has also very good correlation with kappa L. And then two more parameters which we took from the physics of thermal conductivity and build a model based on just 4 parameters. And we generated a beautiful model with an error of 0.21, and the residual was lying within 0 plus minus 0.1. There is a very well-known semi-empirical model, which is called SLAC model, that exists in the community. And this is how, if you use the SLAC model, this is how it does. It does really bad. But then this is not a fair comparison, right? Because this is a model which was found by using machine learning. Now we have another model that is getting generated by semi-empirical method. So what we did, but the formula of a SLAC model is given here. So we picked up these guys as our features, right? Or as our attributes. And actually some of these guys were there in our model also. And then build a machine learning model. And look what happens. Everything falls on the place. So this is, so exciting. You get a goosebump when you see something like that, because SLAC parameters were good, but the relation which SLAC has found was not that good. Okay, I must mention it was not as great as the previous one. Okay, I wanted to just look at a time because, but it did a very, very good job, right? So these parameters were fine. So again, SLAC was not, he's a great scientist, so I should not say anything about him, but he was very much right. His intuitions were right. But this he found not just from intuitions, but from the basic physics and semi-empirical approaches, and they work quite well. But if you add a little bit of machine learning on that, things just become beautiful. So always remember, whatever example I'm seeing, humans are playing a big role, right? So, but things are getting much better and accelerated by use of machine learning. Now, something completely different. So, we need to have, as I heard from somebody, from the moment we get born, our brain makes connections. All these neurons start making connection till we die. And if we can create that unique connection, then we get the Nobel Prize, right? So this somehow got stuck to my mind that, okay, when can we do that? And not every one of us can do it. There are very few people. Many of people do it, but only few of them get the Nobel Prize, right? So there is one thing, when you do electronic transport and thermal transport, you'll not find any theory which connects it. People study electronic transport separately, thermal transport separately. Electronic transport, getting the electronic transport is very easy. But to get the thermal transport is very, very expensive, very hard, very few people can do that. So if suppose I know the electronic transport, can I get the thermal transport? Can I do that? So this is what we took it as another challenge. We created, so we picked up two transport coefficient. One was the Seebeck coefficient, other one was the conductivity. And we applied it to the database which we had. And we created two independent model, one for Seebeck coefficient, other one for the conductivity. We developed nice, beautiful model, which was expected. It's very easy quantity to calculate, so I don't need machine learning for that. I can do it with a normal science. Yet machine learning also does very well, right? Now, what we did, we picked up the features which were giving me this model, right? So those are going to be my linking descriptors. And what we found, very, very simple thing, right? Bond distances. So, and you could feel it, right? If the bond distances are smaller, the overlap of the orbitals are huge, the splitting will be large, the band gap will be large. At the same time, it will have a highly dispersive band, so mobility will be higher, right? So thermal electronic conductivity will be higher. So somehow this bond distance, which is a very innocent quantity, actually end up controlling your transport, electronic transport. Now think on the other extreme. So thermal transport actually happens through the phonons. So it depends on the force constants. So if some bonds are shorter, that means the bonding is very strong, right? So force constants are very, very good, okay? And that means it will have a large thermal conductivity. If the bond distances are large, that means they are weakly bound, your spring constants are very loose, so the phonons get scattered out, and your thermal conductivity will not be as good as you would expect. So they do capture it, right? But we don't have a scientific language or equations to express it. So there was a link between these two properties, and we say, okay, let's try it out. So this is what we did. Of course, I can explain you for all other things which are here, but in the interest of time, I'll just give you the example with bond strength are actually correlated. Volume is also derived from the bond distances. Electronegativity is a little bit out from outside, but the differences of electronegativity actually tells you the bond distance and coordination number. So all these intuitions are the things which I'm telling you where we need human. And when you do that, here's the model, right? So this is the first model wherein you can correlate the electronic transport to thermal transport. Now, the thermal transport which I'm talking about is the lattice part of thermal constant, right? The lattice is the one which conducts the heat most, not the electrons. You can come back and tell me, hey, Weidmann-Franz law, there the electronic and thermal transports are correlated, but that is only for the electronic part of the thermal conductivity, which has a zero contribution as soon as we go to semiconductors or insulators. So what we are talking about is the lattice part of thermal conductivity. So knowing these small thing, and then using, or I don't know if it's small or big, having these intuitions in your mind, that's where I think the creativity comes in. And then use the tools, because you do not know the language, I mean, in which hypersphere or hypersurfaces they connect. But you know the features, the attributes which controls them. So if we can combine these two together, we do wonderful things. So here's another example, and this one outperforms the models which I have shown you previously. Now the learning from machine, this is my favorite part, right? So some of these things requires a lot of resources, right? And I always think from the perspective, even though I do theoretical as well as computational physics, but I always think how an experimenter is going to approach it. So can we come up with some simple intuitive ideas, right? Chemists are very good at it. They have beautiful intuitions, and based on their intuitions, they carry out their experiments. And these intuitions are based on the scientific, hypothesis. So we wanted to do the same thing. And here is just one example I'll give you. Some of these things, some of these descriptors very nicely partitions the data. You see the bands here coming out. That means there is a direct correlation. So if you need something which has a thermal conductivity in this region, you need to have a sigma value in this and bond distance in this range, and you can get the thermal conductivity in this regime. So these important small learning now, which machine is teaching us, which earlier I didn't know that, is another added point which we get from the machine. But we are the one who are interpreting it. Remember that. Machine will not tell you, okay, this high or low will give you this machine. So it doesn't know even anything. Next, I just switch the gear and quickly tell you the last example where we are working nowadays is the structural material. So, aircraft to gas turbine, everywhere, structure. So I told you the functional material. Now I'll tell you the structural material, which we see, steel, alloys. And they are very, very important materials. They, we drive cars. We want to know that their integrity, the structural integrity of my car will not go away if I hit a, some roadblock or tree, a small tree with a low speed. So this depends on their microstructure, their mechanical properties. So now these microstructures, the experimentalists, they get it when they develop a model. Sorry, when they develop a particular alloy or structural material. So what we did, we picked up those microstructure, which are published in the literature, and we use image processing to get the feature out of it. So this is a nickel and cobalt based superalloys. And then what we did, we denoise it. Then what we got, we just transformed it to a to a black and white region. And once we have it, then we use what is known as a connected component. So we use a lot of image processing techniques to get these connected components. And then from that, we started getting the things like effective area, effective perimeter, effective radius, effective compactness. Very simple things. Anyone can do that. And then on top of that, but we don't stop there. We added the elemental, which elements were involved in that particular alloy, what was their composition, and what was their processing parameters. So these things has to come from the experimentalist. My experimentalist friends should give me this information. So they should do these control experiment. And if they do it, we'll give them beautiful model that we can promise. And here is the Vickers hardness, which we calculated with a very low error. So this was one part. The second approach was a statistical approach where we have used the, so once you binarize the image, what you have is just 2 pixels, black and white. So you find the correlation between those 2 pixels and get the, what is called a PCA analysis, principal component analysis, and pick those a few components of the PCs and make a model. You will fail because just using PCA and your machine learning model will not help you. Now what you would do? So then again comes the human. Human is a big savior, right, for the AI. So what you would do, just add a little bit of information of the chemistry of the alloy. Just tell what composition it has, which elements it has, and in what composition, and then magic happens again. You end up getting a beautiful model, which has very low low RMSE. And this is a very important hardness. Hardness decides like how resistive my material is to any kind of a wear and tear. Okay, so this is a very important mechanical property, which any, the structural engineers, they need this before they use a particular alloy. So this is what we showed you. And that brings me to the conclusion of my talk. We are doing a lot of other interesting and exciting things. I hope another chance where we can tell you the other detail. So first and foremost thing which I see is the accelerating the discovery of materials with desired properties. That is already happening in material science communities, as Dr. King has also told you. So people, the thousands of years of work can now be done within 1 or 2 years of the time frame. But remember, we are not as lucky as these internet companies are because our data is very expensive. Their data is very easy, very cheap to get it, and that comes in a huge amount. But our data comes in a very limited amount. And therefore, we must use our intuitions to select what is a good data for us and what is bad data for us, and make the decision. So human decision remains an important factor at every step of our work. Then the aim is to using out the business of science. It's a poor choice of a word, but I do not have any better ideas. So why do we want to do that? Because we want to reduce the cost of doing science. So if we have these development data, if we have these big databases, then you don't do hit and trial anymore. You just go quickly to that database and search for the material which you are looking for. All these automation tools, including those shown by Dr. King earlier. There are in other areas also, active learning has been used very extensively for the development of alloys. And then development of algorithms, the software, the tools. The one I showed you for the prediction of the Vickers hardness, we are going to release it on an. All you have to do, bring in your alloys SEM image and composition. You just feed it to to that model, and it will tell you what is the Vickers hardness in a fraction of a second. So this is already done, the GUI, but it's at the lab level. We have to release it soon, and we'll be doing that. And the last thing I did not have much time to talk about is the discovery to knowledge, right? That was the title of my talk. So unraveling the hidden connections, which I showed you for the case of electronic transport and thermal transport. So these are, so, you know, the role of a human is to take the AI to the areas which nobody has earlier thought of. That job AI will not do. So selection of problem is still lies with us. And the choice of the problem makes a Nobel Prize or not. So will AI ever win a Nobel Prize? Alone it cannot. The answer is no, but it will definitely help because it's an extremely powerful thing. It is so exciting to do research when you have a tool which AI gives you, because you can build on hypothesis, essentially the choice of problem, and use AI. It will do things far more faster than, you know, the traditional scientific approach. So I believe AI will definitely help, but will it ever win a Nobel Prize? I think the guy who will make Dr. King will win, because he's the one who got the Adam, Eve, and all these automated systems. So how much intuitions which he has feed in to get what Adam and Eve today is doing, you know, that gets the Nobel Prize probably, right? So computer does exactly the same thing what we ask it to do. It looks at the face value that it's very exciting, but it has not done anything which we have not asked it to do. So with that, I'll stop, and thank you very much for your invitation and your attention.
Wow, Dr. Singh, thank you so much. That was absolutely fascinating. If I may just ask you a question,
Sure, please.
just purely from my own sort of selfish need or understanding, I'm fascinated with I guess the quest of material science, and how machine learning and how it can be used as a process of discovery, and the relationship to maybe less error-prone quantum computing, whether that's through trapped ions or superconductors. I just wondered, either with the sort of the next generation of computing, we're looking at either more accuracy in quantum computing, or we're looking at replacing silicon with something like graphene. I just wondered, you know,
very interesting question. So thank you for asking this question. This brings it to our recent interest, and that comes from my background in the defect physics. So I worked only for one type of qubit. So quantum computation area is really vast, and I think one of the authors will talk about other things. But there is one type of the qubit which is called a NV, nitrogen vacancy in carbon, which is a defect in a diamond, and that is considered as a very good qubit because it matches all the recipe a qubit should follow. So we'd like to do that, but diamond, you know, and there are certain issues which, so again, the same recipe which we have been using, we can apply now to search for a newer material, not just going to the diamond, which requires a high purity and very expensive. So can we find some other host material which can host these qubits, having all the properties which are required to be called as qubit or a stable qubit? So that is one part. Now, circuit design for the quantum computers, you know, AI is all the way there. All the time they are there and they're helping and developing I mean, once you have this qubit, what kind of a circuit you will design to do a particular job, that is completely done by neural network and some other act. So I'm not really an expert in quantum computer, but just a small bit of things which we are doing. And that is, again, I told you, because of my background in defects. But yes, the circuit design part where the machine learning is going. And now for the machine learning itself, once you have the qubit, can you come up with the algorithms which can be applied easily on the qubits? So these are the three major things wherein, you know, machine learning, human machine learning will go hand in hand and probably help to take the quantum computers to the next level.
Thank you. We have a question in from our audience.
Yeah, sure.
Hello, Dr. Singh. What should universities train students for, given that working with ML models is becoming the norm in so many disciplines?
Very good question. And this was one of the point I wanted to put it in my conclusion. So machine learning, and please do not get offended when I say that, it will become uh, it will become almost like the basic training, right? Where so suppose you have come to your undergrads, you have learned mathematics, physics, chemistry. Machine learning also has to be taught now, because without this tool, it's becoming indispensable now. So we cannot say that, okay, I don't know machine learning. So even you are experimentalists, I mean, and Dr. King has showed you that those experiments requires, and it's good to know what it is, right? And don't use it as a black box, because then it's no fun, not a fun. So of course, if you go to internet, you can download as many, just go to the GitHub and you can get so many different kind of codes. But if you don't understand what you're doing, then you'll not enjoy it. It will become very boring for you, and doesn't require much. You need to know you should be good at maths, of course, especially in the probability. A little bit of statistics and some knowledge of computer science would equip you so that you can go and start using it. It is an important thing, which I mean, for India perspective, for anywhere, now we must learn it. As a, when we do the theoretical physics, we must know the mathematical physics. It's a must for that. Similarly, now for science, I believe machine learning or AI is a must. We can't
Thank you
avoid
very,
it. Yeah.
yeah, thank you very much.